Welcome everyone to the last but certainly not least event of Wayne 2021, which is the Research Academics panel. Thank you all very much for attending. I'm really looking forward to the coming hour and the great discussions with the panelists. What I will do is I will share a few slides in the very beginning just to set the scene a little bit. And then we'll leave the floor to the panelists. And while I am presenting, what I would like to do is to invite and encourage everyone to start putting questions to the people on the panel in the chat. I will be basically facilitating the panel and will be asking the questions on your behalf as part of this. So I think many of you or some of you will know me. My name is Jan Bosch. I'm one of the organizers for the workshop. And the panel, I will ask them at the end of my presentation to briefly introduce themselves, consists of Jane Cleveland Huang, Brian Fitzgerald, Barbara Plank from IT University Copenhagen, Ipek Oskaya, and Ian Gorton. As I mentioned, after my brief introduction, I will ask each of the panelists to introduce themselves so we can get a little bit more background on their relation to the topic. What I wanted to stress, because this is one of the questions that has been brought up in some of the conversations around the topic of AI engineering and why we push for a topic around AI engineering, is often I bring up this slide, and I've annoyed quite a few people with this slide. But basically, what you see here is a doghouse, in this case for a dog called, I think, Jessie or Tessie, depending on how you're interpreting the first letter, and a high-rise building. And if we look at the difference between the two things, on the one hand, if we look at building doghouses, it is basically a small scale. It involves relatively few people. It is very much concerned with pilots and prototypes. There is no or very little societal value, to be very honest. And in practice, there is really not a lot of risks when you're building a doghouse. And when you're building a high building, well, we're basically talking about very large-scale development. We're talking about hundreds of thousands of people involved. We're talking about industrial critical deployments. We have a high societal value, but we also have a high risk associated with this. And to be honest, I've spent half my professional life in industry and the other half in academia. To be very honest, my view is that most academic research tends to be concerned with building doghouses. So a small scale, not a lot of risk, and to be honest, not a lot of value. And typically, the focus is on studying the applicability of technology. On the other hand, if we talk about engineering research, we're talking about the research required to effectively and efficiently engineer the solutions that we're talking about. And this is typically concerned with studying the benefit and scalability of solutions in an empirical real-world context. And I suppose why I'm bringing this in the context of AI engineering, because to be honest, I look a lot into what is happening in the AI world, and a lot of the work in AI is concerned with finding a tweak of an algorithm that happens to work a little bit better for a highly selected data set, rather than really effectively and efficiently helping companies to apply AI in a better context. So for us, AI engineering is bringing everything that AI has to offer from the left side of this picture to the right side of this picture. If we, however, look at, because the other question that I then get very often is, why not just lump this under software engineering? Why coin a new term called AI engineering? And yes, you could view AI engineering as being a subcategory under software engineering. But if you look at two of the studies that we have been looking at in order to identify what are some of the challenges that companies experience when they work with machine learning systems, then you see that there are a number of topics that you don't typically see come up in traditional software engineering work. Things like the whole notion of that many systems containing AI solutions have a lot of glue code and lots of supporting systems around it. that we have to deal with cultural differences between data scientists and software engineers, that the transparency of the models that we come up with and what we deploy is often quite limited, and that is viewed often as a challenge, and often it isn't quite clear why a model performs well or does not perform well, which leads to a situation that troubleshooting and testing is actually surprisingly difficult. And in real world deployments, you can very easily get unintended feedback loops. So this is work that for those of you that were in the industrial panel during the lunch slot or right after the lunch slot, is one of the co-authors. He was in that panel, and together with Peltalion, we did research on some of the challenges that they were experiencing in the 2017 timeframe. The paper was published a year later. More recent work, one of the organizers, co-organizers, Lucy is the lead author on this one, lists a number of machine learning challenges that companies run into when we look into real world industrial settings. So we did a review of the literature only focusing on machine learning and deep learning papers where there are actually real world industrial deployments, and what we see is lots of challenges around adaptability, around scalability, around privacy, around safety. So it is clear that there are quite a few engineering challenges in the case when we are adding machine learning and deep learning models to systems. So this is why we believe it's so important to have research going on around AI engineering, and I think that this is also why many of you are concerned with participating in a workshop and have identified that this is a big topic of interest for many of you. So what I now want to do is to end the introduction and to basically ask the panelists to introduce themselves. And since we have 3 women and 2 guys, 2 gentlemen in this, if I could only find my mouse here on my screen, there we go. I will stop sharing the screen, and I will basically point out people as they are appearing on my screen. So Ipek, I was hoping to ask you if you could start with introducing yourself and sharing some of your issues or some of your views on the topic at hand.
Sure. Thanks a lot for including me here, Jan. Ipek Özkaya. I'm at the Software Engineering Institute, Carnegie Mellon University. My personal passion and research is architecture and technical debt, and add AI and ML to it. It's a perfect mix. In our group, we work on across the board, but most recently, one of the things that we've observed is, I would really like to disagree with you, but in this case, I cannot. It's one thing to develop models in Little Lab, Jupyter Notebooks, and test with the data that is in the open source. It's another thing to deploy them and sustain them. And our customer space is more government as well as more regulated industries like healthcare, banks, as well as government industries. And they're really, really challenged in terms of understanding what that life cycle looks like. How do I really make AI elements as part of the overall system of systems and be able to really anticipate some of the failure modes that I will perceive in the long run? So maybe I'll stop here to give my panelists another chance, and we'll come back to some of these challenges as we discuss further.
Absolutely, very nice. Thank you very much, Ipek. Ian, since you're furthest out and you have bursts in the background, maybe you go next.
Yeah, apologies everybody. There's lots of tweeting birds around me at the moment. I'm Ian Gorton. I'm a professor of computer science at Northeastern University. Even though Northeastern's a Boston-based institution, I'm actually based on the Seattle campus. And so I live in, my office when I'm there lives in an area that is surrounded by the center of the cloud computing world. I've been working with AI and technologies and architectures for way over a decade. I worked in scientific research, and we used to work with data scientists and computational scientists to build machine learning pipelines for all sorts of scientific applications. So this is something that I'm pretty familiar with, and the many challenges both of doing the research to get sensible results and then actually deploying the system with and all the sort of inherent glue code and stuff that you have to write and the provenance that you have to keep. So that's my world anyway. Over to the next one.
Excellent. Thank you very much, Ian. Barbara, since you're close, Copenhagen, and maybe you want to go next.
All right. So thanks a lot for the invitation. It's really my honor to be here with all of you. So I'm an associate, soon full professor at IT University of Copenhagen. I'm a researcher in natural language processing, machine learning, deep learning for language processing, essentially. So I come a bit from that side to this panel, and I'm also the head of the data science master that we are starting here this fall. So I bring also this educational interest to the table, which many of you share, but would like to highlight that that brings special challenges in the sense of what we teach our students as well in these times, right? I'm very interested in general about making about many things in NLP, but about making them more robust to issues like data shifts to new languages, supporting scaling it up in the sense of making NLP more broadly available to the world. And that brings a lot of challenges. And one of the challenges is the fact that often as academics, we don't have the data sets to even benchmark against real situations. And at the same time, then the software engineering part is going to be, I think, very important in the future, that different fields communicate much more with each other. So I'm happy to be here to engage with you.
Thank you very much, Barbara. Brian, you want to go next?
Hi, Jan. Yeah, so I'm delighted to be here as well. Looking forward to this panel. My name is Brian Fitzgerald. I'm director of LERO, which is Ireland's National Software Research Centre. So we have about 300 researchers across 12 institutions. And we have a lot of projects with industry, probably over 100 projects with industry partners that are contributing about $30 million. The domains we work in are autonomous vehicles, for example, smart cities and healthcare, all of which have strong AI components. So there is huge interest, I think, in companies in applying AI or leveraging AI. Examples of work we're doing are around image recognition in autonomous vehicles and also in healthcare. So, for example, examining X-ray mammograms for cancerous lesions, we can, perform better than radiographers in identifying suspicious lesions, outperforming medical experts, or identifying the surgical instruments that are gathered during an operation to make sure that none are left in the patient when the operation is complete. Just scanning the bin to see they're all there. Also, applying AI techniques to improve testing, for example, that was mentioned in the workshop, I think. Generating programs to run in parallel processors and doing that better than human experts. So we have a lot of different areas in which we're applying autonomous systems. I think there was a really nice quote from Grace Lewis yesterday about I think it was effectively that companies have a lot of data and looking for ways to leverage and monetize that. And we certainly find that either through sensors or through logs. Companies have a lot of data and they're expecting to get some clever ways to leverage it. And it's not as simple as that, I guess. So I will leave it there. I think there are a lot of challenges that have been surfaced at the workshop. I'm happy to talk about those in the next part of this panel. Thank you, Jan.
Very good. Jane, you want to go next?
Sure. Hi, everyone. I'm Jane Cleland Wong, and I'm a professor at the University of Notre Dame, which is in Indiana. And it's been a great workshop so far. I hope it will be after this hour. So my experience in software engineering for AI has really been in two very different areas. I've been researching over the last couple of decades in the area of software traceability and its support for safety assurance. And quite recently, we've actually achieved some really good results in automated tracing using AI techniques. So this is kind of one of the examples of using software engineering for AI. But actually, as part of that project, we struggled in something that many academics struggle with, which is in actually having good data sets. So I guess about 4 or 5 years ago, we decided to build our own system, which is basically a system for multiple semi-autonomous unmanned aircraft vehicles for use in emergency response. And this project has kind of taken a life of its own. We have had funding from NSF and recently new funding from NASA. And actually, both of our projects are in the process of commercialization efforts. So we've been looking, very specifically at how not just the academic side of it, how to get that doghouse to be those high-rise apartments. And so we've been looking at some of these challenges. And in particular, one of the areas that my team has been looking at is the intersection of humans and AI agents. And I can talk more about this later on, but I think it's a particularly interesting aspect when you have kind of human intelligence and artificial intelligence kind of working together. How do we engineer systems that work in that kind of domain?
Wonderful. Thank you very much, Jane. This is where I would like to encourage the audience to start putting questions in the chat, so it doesn't become a conversation just between the 5 of us or the 6 of us, but actually something that is an interaction between the audience and the rest of us. But while all of you are thinking hard and typing in questions in the chat, maybe I'll start by a very generic, open question, which is for each of you, what do you view are the key future engineering research challenges for software systems, including AI? If you would like to see papers at next year's instance of this event, what kind of topics would you like the community to address? Let me put it like that. And you can raise your hand or just start talking on, depending on how you want to do it.
I can go first. I was the last, now I'll go first this time. So I always approach these problems as well from thinking about the requirements perspective. And as I just mentioned, I'm particularly interested in the intersection of human and artificial intelligence. Just to provide a bit of background to that, some of you may have heard Sophia's talk a little bit earlier, and we are basically looking at how do we know when we can trust the AI component to make autonomous decisions that kind of seriously impact the effectiveness of the mission, and when should humans be engaged in that? And our vision actually for emergency response is that humans and machines work together as true partners. And to understand how those kind of things are going to work from the software engineering or requirements engineering perspective, we have to, really understand how much we can trust the system, and have, kind of quantify that in a way that, and also understand the requirements of what people that are going to use the systems really want. So I think one of the, the big open challenges is thinking about the contextualization of our systems. And I'm talking about drones here, but it applies to almost any AI system. Who are the users? How will they know whether they can trust the system or not? And also the reality that the systems won't always be trustworthy. So how do you provide the users with a situational awareness that they need so that they can make kind of quick or longer term decisions about trusting the system? So I would say one of the open challenges is at this intersection of kind of human and artificial intelligence, and how we engineer systems to support that.
Lovely. Thank you very much.
Echo some of those comments, if I may. The requirements for intelligent systems are really hard to settle on. We've been doing some work in a couple of projects with small companies, and they have really nice problems that we've been working on, but they expect the world in 6 weeks. They want to do incredibly intelligent processing of this data, and it's just not possible. The technology's not there, and the engineering's not there to do it so quickly. So I think, maybe this world might breathe some life back into requirements research in software engineering, because that's a pretty dull world nowadays. Maybe this makes it much more interesting.
Yeah, Brian, sorry, ladies first normally, so Ipek.
So some of the work we do with my dear friend and colleague Grace Lewis and our team members involve doing retrospective studies for organizations. They come to us and say, well, we've done this. Yes, we have an AI system, but the process was very painful. Could you please help us what we could do wrong with what we did wrong? And we find over and over again, it actually boils down to how those systems are architected, and interestingly, how they're tested. I think today we don't know much about how we test these systems, especially with this uncertainty and emerging requirements involved with the data aspects of it. And there's a big gap there, as well as how they're architected, because there's so much technology and infrastructure out there. We rely on the cloud, we rely on all these frameworks, but at the end of the day, there are some of these gotchas that the organizations find themselves within a little too late. And these are the things that our researchers don't necessarily look at because they're more on the engineering side of things. But I think that would be a nice opportunity to bring the academic as well as the engineering aspects together.
Great, thank you. Brian.
Yes, so just echoing what Ian said particularly, I think companies are looking for solutions. They do underestimate the challenges, though. I think that you can marry AI and SE. So, like, SE has had 50 years to get some discipline, I guess. AI techniques are not like that, and like, so we find one major challenge is like the AI part is very much like a waterfall. Something gets produced, but trying to marry that with an agile sprint cadence is really difficult for companies because it's too different. And there's a quality issue with stuff being developed in a waterfall model. Then you don't find errors till much later. So that they're very different disciplines. I think that people, I think, underestimate the challenge of combining them. Not in this workshop probably, but in general, it's not. It's assumed to be fairly unproblematic. And I guess the same thing with in the early days, people were overly optimistic about how successful they could be. It's very, very difficult to marry these two disciplines, I think. And that would be, there's a whole lot of work to be done on delivering that, I would say.
Very good. Barbara.
Yes, so many good points. So I would like to maybe come back to some of them. I think especially evaluation is something which is at my heart as well, and it's at the core of machine learning in general, but also especially NLP, because we are essentially facing human data, right, making sense of language. But one of the challenges is also to get the expectation right, and that ties to, if the consumers or whoever wants to use AI, that there is, like Jan said, they want the big system to solve the problem in a few weeks, which is completely unrealistic on the one side. But then also this lack of understanding how we evaluate currently, the measures we use. Sometimes, it's very hard to communicate them easily even for us, it might be obvious, but to bring this sense of what does this metric even mean? Is one metric enough? How can we bring the user into this? How can we create better evaluation metrics that are more tight? I think there's a lot essentially also close to software testing practices that AI disciplines can benefit from. I see some of this now entering NLP, but there is much more to be gained in better evaluation and making that a central theme of anything close to AI.
Very good. Thank you. I will jump to the chat and pick up the first question that came in by Lionel Briand. And he raises the question of integration strategies to embed ML components into systems. I mean, how do you do that? And that's not just purely from a software integration perspective, but also from a perspective of the certainty that comes with ML models. And should we actually be, how should we think about that? Because, I noticed that in many of the cases, people seem to assume that requirements-driven software is perfect and does not contain any errors, and we really have to struggle with the F1 scores that machine learning models provide, basically causing a situation in which we only have 95% accuracy, so 1 in 20 answers is going to be wrong or off at least. So can I ask you to comment on that? How do you think about the integration between machine learning and traditionally developed software? Who wants to go first? Ian, I think, unmuted, so I guess he has something to add here.
Yeah, the birds have got something intelligent to say. One thing we found is the scalability issue and the cost issue is a really subtle and important thing to think about. We deployed some models for one of the companies we work with, and we deployed them on various configurations on AWS. And it was a real experimental process to actually get to a configuration that was was efficient in terms of the quality of service it provided, and also the cost that that it was incurred. And it was very unintuitive how to do this with the models. And so I think that's a really subtle problem that we have to think about. And it's obviously got something to do with the complexity of the models and the actual AI models that you're using. But it's really hard to predict how they use the underlying infrastructure. Plugging them into sort of a data processing pipeline is not that difficult, but the actual planning is really hard.
Right. Thank you. Anyone wants? Yeah, Jane, go ahead.
Yeah, so I think, you know, just thinking about our own UAV system, I mean, we engineered this in a very traditional software engineering method approach. So we have an architecture, we have all, you know, we know our requirements, but we have some AI components that are in it. And I think that, you know, really around, and as we're gradually introducing the AI components and kind of adding more, kind of increasing amount of AI around it, we basically are putting safety monitors there. So, for example, if a drone finds a person and goes into tracking mode, first of all, it uses vision to find the person, and then it uses vision for tracking. But there's a certain amount of uncertainty about GPS location, about the actual imagery. But we have to put kind of safety monitors around it so that we feel comfortable experimenting with the different, with kind of new forms of AI components that we're using there. So I think that's kind of the approach that we've taken. It's traditional and that it's incremental, but it kind of allows us a safe way to experiment with our AI components.
Great. Yes. Of course, it does require that you are able to identify when something is an unsafe or a safe action, I suppose. But that is definitely something you can do. Any other comments that people want to add, or should we move on to the next question? Ipek.
I think one of the things that we overlook very often is we assume that without AI components, the systems are easy to integrate, there's no uncertainty and whatnot, and add on to it the AI component. And I think what that creates is explosion of complexity. So maybe starting small to the extent we can will help in terms of learning and double testing our assumptions.
Yeah. Yes, yeah. I've noticed that many people that I talk about within these concerning these changes seem to assume that traditionally developed software is perfect, error-free, almost free to build and easy to maintain. Whereas in practice, of course, we all know that that's far, far, far from the truth. Which brings me to the next question by Helena, one of the organizers. And that was that in the industry panel, scalability was mentioned quite a bit. And this is, of course, one of those doghouse to high-rise building transition topics that we're raising there as well. So how can we, from an AI engineering, software engineering, or research community perspective, help the industry scale the deployment of AI systems? I mean, what should we be focusing on? And as you think about how to respond to this, please also be clear on, help us define what you mean with scalability. What are you looking to scale? Because that is also a topic that can be interpreted quite widely.
So scalability is an area that I play in, and I'll just do a plug for a book on O'Reilly that might be popping out in the next year by yours truly on that topic. Well, one of the issues with scalability is making sure the models perform efficiently with larger collections of data. And so it's one major issue that we found. And obviously this depends on the algorithms that your model's using. If you can train a model so that it can then give you a constant time response to any query, such as an SCN type model, then that's great. But some models don't behave that way. And so I think there's an inherent necessity for architects and engineers to understand the computational complexity of the actual algorithms themselves. You can't get away from it. As the amount of data grows, then you've got to understand how that affects the scalability of your solution.
Right. Thank you, Ian. Ipek, you were also raising your hand, I think.
Yeah, I think this is where the academic research needs to grow up, very quickly, very fast. There are very, very few pockets of, I think, research that really understand the industrial scale scalability challenges. And it goes to the infrastructure we do our research in, it goes to the number of people that actually need to be developing these systems and the number of users. That's a whole different level of scale. And I think that's where the doghouse to skyscraper comparison really, really holds. I'm not sure what the right answer is from a research perspective, but at least awareness that the scale challenges for industry are significantly different than the scalability papers and research we talk about. That's just an observation, neither here nor there.
Yes, except that Ian will be writing, right? Or is in the midst of writing. I mean,
well, as I said, there are few pockets that do it. So
yeah, exactly. No, that's true. Anyone? Yeah, Barbara, go ahead. Sorry, Brian, I didn't.
I would like to bring in actually maybe a bit of a critical view, because I don't know if we all should go to the skyscraper house, to skyscrapers. So I'm clearly sitting on the dark side perspective here, of course, but on the other hand, this is a big trade-off, right? It's a trade-off between being able to run big systems versus the accuracy also they get. And here, especially in NLP, we've seen, every one of you perhaps has heard about BERT and GDP3 models, I guess.
Yeah. Yeah.
And the problem is in academic environments, these models are not runnable. So how can we, I would actually put the question back, how can we get academia even to be able to compete in this, setups without going into industry? Is the only close collaboration with industry even the only way about going that way? So I would like to maybe raise this question a bit on a critical eye, because now it's all about bigger models, but that's not the future for everything, I believe. We need also some research in smaller areas, more scalability areas, which earlier on were actually mostly on the industry side, but they, out of necessity, also enter more and more in academic questions and setups. While I completely agree that the scale is, absolutely different in terms of users and data and so on. But scaling in our area also means not just bigger data, but also scaling around, for instance, the languages we support currently. It's a small set of a number of total languages out there, and scaling to even, scarce data setups is a big important part. So it's scaling up to data size, but scaling broader. So widening up is kind of part to the scaling, at least in my sense here.
So, can I play back to you before I let the others in, Barbara?
Absolutely.
I mean, now you mentioned that you work a lot in NLP and related topics.
Yeah.
And you mentioned BERT2, BERT3, etc. I mean, those are huge models that I think cost something like $5 million to train. They have a fantastically large GPU network behind them to get trained. How do you do research in that area when you do not have access to that kind of infrastructure that others, the companies, clearly do have? Because I think that would very easily become problematic.
It is. It's actually so around NLP, which is unsolved, right? Luckily, we have many unsolved problems. But in a way, there is also a flip point to the industry side, which brings academic research into more homogeneous area than it used to be. So we have much more now BERT kind of models that are applied to research problems. So it kind of is like homogenizing research, because now that's expected even if you publish.
Right.
How we do, I mean, we can do to some degree still in this, BERT-like models. We can train some parts of it, but we are clearly, that's not the main interest, right? Running a model on weeks of data, this is not so much of an it's nice that we can then analyze what comes out and think about the societal impacts and so on. But if every NLP research lab would try to do that, we would just everyone would do the same kind of research. So it's good that we all focus on different questions.
No, but I mean, the point is that, we all hear about the drunk man who is looking for his car keys under the streetlight. not because he lost them there, but because that was the only place where he could actually see anything. Yeah, so I mean, it easily becomes that we do research in the areas that are feasible rather than the research areas that are the most important. And I'm trying to find that balance because I mean, of course, NLP, there's a fantastic amount of text in the world, natural language text that we would want to do things with. And that's why I'm so curious. I mean, how do we make sure that also as academics we can focus on the most important problems from a societal perspective, rather than on the problems that are feasible to study from an infrastructure perspective? And that balance I'm trying to understand a little bit better.
All right.
If we move on, Jane, you were unmuted, I think. Were you looking to jump in?
Yeah, I could just add something to what Barbara's saying. So we actually had an ICSI paper, or one of the people that had a paper that used BERT and applied it to traceability. And I think one of the things that software engineers tend to do is to take some of the existing AI approaches and NLP approaches and then apply them to very specific problems. So I think that's, so yes, it's difficult for us to train a model from scratch, although it is possible to do that with, resources from the university for specific areas. But I think apart from that, we use this is more AI for SE anyway. But basically, I think that there is a lot we can do in kind of taking some of these approaches and then applying them into software engineering. From the actual going back to the SE for AI, I'm not so sure that it's it's more, I guess, AI for SE in that respect, though.
Yeah. Good. Thank you. There are questions falling off the chat because we have a quite active one. So I know that I missed one on green AI, which I'm maybe going to come back to later. But there is a topic at the top of the chat right now about AI explainability, which I think is an interesting topic because I meet two camps. The one camp is basically saying, if you can't explain how it works, it should not be in my system. And the other camp says, if it works, I don't care why it works, I just care that it works. And I'm basically putting it in anyway. And I'm trying to understand from you esteemed panelists, how you're viewing the AI explainability problem. How important is it that we're able to explain how or why a model works, and in which cases is it particularly important? Anyone wants to jump in?
Well,
go ahead.
Certain models they're just black boxes. They give you an answer and there's no way you can understand how it comes to that answer. So, if you've got a black box model, then you've got that, it's a problem. You can't do anything about it. Someone who I hired years ago went on to work for Microsoft in the Bing security cloud team, and their job was to stop people trying to attack Bing, and they used AI models to do this. And one day they managed to block half the world from accessing Bing for half an hour because their model was not quite correctly trained. They'd no idea how. They obviously just opened up and got it working again until they could deploy the model that worked correctly. So yeah, it's a problem, but I think that isn't that linked to I'll ask the AI experts on here, but some models don't give you any explainability. So yeah, that's life.
Yes, go ahead, Brian.
Yeah, so just on this, I guess I can see the arguments are easy on both sides. I guess I can see arguments on both sides. Like years ago, there was a psychological research which showed that the best predictor of success in the armed forces in the U.S. Army, I think, was if you wore a uniform as a child, if you were in the Girl Guides or Boy Scouts or something. So you could, or the best predictor of door-to-door salesman success, or kind of, you knew what the best predictor was. You didn't know why it operated like that. That didn't matter so much. But I think the transparency is important. So we had some research recently which looked at the MIT Tiny Images data set, which is 80 million images that have been used to train an awful lot of AI systems. And they were found to contain racial and gender stereotypes, which now the system has been taken down. That data set isn't there. But if you don't have transparency, at least to know why, what what kinds of how decisions have been taken, then it's very dangerous, I think. So it really is important, I think, in this case, to have more visibility and transparency. On balance, that's more important, I would say.
Jane?
So I think there's, you know, I think explainability and transparency is really important, and more so in some areas. I think, you know, I said we have two areas that we're working in. One is traceability. You know, the user sees those results, they can judge those results, and honestly, if those results are correct, then they're going to trust them, and that might be okay. But I think there's other areas that, you know, if it's in a kind of autonomous system and the system's making decisions based on that, you need to know why. If it's doing something and it's different from what you expected or anticipated, you need to know why. Because, for example, in a human on the loop system, you need to be able to intervene if it's doing something that's wrong. So maybe it's a surprising thing that it's doing, but it can explain why it's doing it. And maybe it's a surprising thing and it's doing it for wrong reason. So I think that there's, you know, explainability that's like, now, tell me now why you're doing it, very quickly. And then there's others that's kind of longer term, where explainability can be over a slightly longer term, like, why are you saying that this person should have this prison sentence? Right. You know, that you can kind of examine it, you have time to look at it. So I think there are these two different kinds of explainability related to situational awareness or kind of more post-mortem understanding.
Anyone who wants to expand on that? Because, I mean, I'm trying to figure out what is a good way. So basically what I hear you say is, I think I heard something along the lines of it depends. It depends on the situation, and then it can be per instance, per inference, or it can be per over a sequence. Yeah, you've now, I don't know, sentenced 100 people to prison through using your AI algorithm. Why do you on average give people 6 months and 2 weeks or something like that, right? I mean, that could be one of those questions rather than every individual case. Anything that you want to add to this, Ipek?
And I think probably the techniques and questions that we apply changes based on the artifact we're looking at. Building upon what just Jane said, there's the data, like you can actually figure out the explainability by just analyzing data and the biases in the data versus the unexpected effects based on the algorithm versus the unexpected effects based on the overall system versus unexpected effects when the user is interacting with it. I think the techniques and the explainability boundaries are different based on the artifact in question. And maybe because we're so excited and also nervous about it, we might be conflating too many things under the same umbrella rather than understanding what we're really referring to when we talk about explainability. The timeline of when you need to know the decision, how the decision was made, is also related to what kind of an artifact is important to analyze based on the explainability aspects.
I think that's a really relevant topic. Okay, I want to change course a little bit and talk about organization. I mean, one of the topics, actually I have a blog post waiting to be written, which has the title, "Do you work with an alien?" And what we've noticed is that there is quite a bit of cultural differences between traditional data scientists, software engineers, and other skills within an organization. And what we see is basically two approaches. One is where all the data scientists are lumped together, all the engineers are lumped together, etc. And then other approaches where people work in much more cross-disciplinary or cross-functional teams. Do you have any perspective on what the best way of organizing is and what your experiences are with the different pros and cons of different ways of bringing these people together?
Got lots of experience working with data scientists, and they're typically the main experts in the area they work in, and they know how to write lots and lots of unreadable Python code, which produces, you know, interesting results, which, you know, we don't understand the domain particularly, but they tell us the results are good. And then they give you this Python code which contains functions of, you know, 724 lines. but you have to then make operational. So that's certainly a challenging world to live in. But I think it's very, very common from what I've seen. Data scientists live in their own bubble and then just throw code over the wall and say, make it work.
Yeah, go ahead, Deepak.
So the work that Grace presented on ML mismatch, I think it touches upon this. It's like, yes, there are different worlds, but there needs to be some way of bringing them together, because then we have the throw around the wall challenges that emerge in the teams.
Yeah.
We see exactly what Ian referred to. I mean, data scientists say, well, I know I'm not a software engineer, but I know how to write this Python code, and I know the software engineers will have to rewrite this, but then it introduces all these challenges. I think we saw this similarly when we had security come into, usability come into our software engineering problems. At the end, everybody needed to be one team. I think that's will have to happen in the near future to be able to get ahead of the challenges.
Jane.
I can add just one thing. One of the students from my group, Sophia, gave a talk this morning, and she was from the Vision group. And this is a project. So this is an academics panel. So this is kind of about research teams, but I think it's a fair comment too. So our team has half Vision people and half software engineers, and we really struggled to kind of find how to kind of work really well together, because the Vision people are caring about slight improvements to the algorithms, and I want our system to work. I want the drones to fly. I want them to find people. And so I think these are really important things. If you find yourself on a team that includes any kind of data scientist or AI kind of expert, and working with your software engineering team, to have these discussions and to make sure that you establish common goals, because otherwise we were going, yeah, we're publishing good, Vision papers, but we're not kind of getting that middle bit. And in fact, our paper at this workshop was our attempt to try and find middle ground and really find a way to work together. So I think this has to be explicit, and it doesn't actually happen naturally, even in an academic setting.
Barbara?
Just second all said so far, especially Jane's experience. I think it would be very, just bringing many different people, even in the education side, like in a data science education, that they don't only make projects with their own data science students cohort, but reach out to other faculty and do projects with software engineers or humanities or whatever the university offers, so that there is much more interdisciplinary right from the education already. I wish we had that in our educations even, much more, because that's going to be the way forward. I think even us, I'm very happy here to hear, about your perspectives, because I think there's so much to be learned across disciplines, also from software engineering, software testing, and NLP or whatever. We can certainly come up with a lot of exciting topics to brainstorm together.
So I am a little surprised that the word ops hasn't come up yet, because we all know DevOps. I'm sure, have all worked with or been exposed to data ops, and now we see AI ops or ML ops come up. And a way of working where I first have the data scientist experimenting in their little work notebooks, the Jupyter notebooks, and then throwing things over the wall to the software engineers to build things, works if you work in a more of a waterfall style approach. But what I'm seeing is that many companies, especially on the software as a service, but even on the embedded system side, are moving toward is a situation where machine learning models are updating at the same frequency as the rest of the software. So every 2 weeks, every 4 weeks, there is a new version of all of this pushed out. And I don't see that work in a more traditional, the data scientist throws the Jupyter notebook over the wall to the software engineers kind of model. Anyone cares to expand on that or comment on that? Not really, I can tell.
Yeah, and I think it probably depends on the maturity of the organization. I mean, I know certainly people in Amazon or Microsoft are working exactly as you describe. But I think to do that, you've got to have a problem that's tangible and solvable. you can't start experimenting in an MLOps style and start pushing out stuff that's still really experimental, and you don't know if it's going to produce good results. So I think once you've got a problem that's well defined and you know the algorithmic approach you can take, then you can actually do that kind of constant rollout. But there's a phase when you get the data. We were working, the 726-line Python function was a climate scientist analyzing data from instruments from the last 20 years, trying to find days when there was the cloud in front of the sun, so they shouldn't analyze that data. And it was a huge data set. It was a petabyte data set, and it took him a while to do it with his 726 lines of Python. So there's different problems, different contexts I think we've got to be aware of.
I think that's a fair point. Deepak?
So we actually have this year started a couple projects, research projects on understanding the ML ops and that pipeline. There's a lot of tooling out there, but our data scientists, ML engineer colleagues warn us that life cycle that is proposed out there is not necessarily complete, and what actually information needs to be collected to bring back to different parts of the process is important. So hopefully as we progress more, we'll share some of our results here in this forum and others as well. But I think assuming that the tools already do it, put it in a container, throw it out, and it's going to solve your problem is a naive way of looking. I think that's what I see mostly in a lot of the industry, as well as some of the process perspectives. Understanding what are the interesting research questions is to actually be able to help industry in terms of how that life cycle might change.
Yeah, great points. Anyone wants to add anything? If not, then we go to the next topic. Roland Weiss, who was a panelist in the industry panel, raises the point, which I think was also made in the keynote by Errol Koolmeister from H&M earlier today, which is that the number of, or the availability of experienced data scientists that can actually create high quality machine learning and deep learning models is highly limited, and mostly working at some large American companies in the area where Ian is working as well. So the question is, what is your view on creating models by non-experts? So I mean, people talk, of course, a lot about low code, no code, talk about AutoML. There are other approaches that we've seen, but I'd love to hear your perspective on how feasible is it to create reasonably well-performing machine learning models if you're not an actual expert in the field. So as what we called at Peltanion, semi-competent data scientist is, I think, the term we coined at some point. Everyone is smiling, but everyone's keeping themselves muted as well, which I think is funny. You're still muted, Ian. Yeah, go ahead.
I mean, I can go to Amazon Marketplace and download models and use them. But no, I think I'd rather work with competent data scientists than random users trying to deploy models. Sounds dangerous, apart from in the most simple and safe environments.
Yeah.
Yeah, I kind of think it is. Well, I feel the same as Ian, that that somewhat trivializes the problem. That people underestimate how difficult it is to write good software. Have always underestimated that, and we have like we don't have anything like modularity, for example, in models that you can combine models from different groups in different areas, and it seamlessly can be integrated into some kind of functioning whole. We're a very long way away from that. So some of even the ML ops, I guess, is premature. We're not really able to combine the development parts, even at the front end of that, into something that is trustworthy, I would say. So I'm less optimistic about taking on models like that, I guess.
Jane?
Yeah, so I definitely agree. I want, experts to design and, the models. However, I also think that, for example, in our traceability area, I said we're kind of doing we're building a tool for commercialization, and we plan to, you can tell me I'm naive here as well if you want to, but we plan to create a wizard that would allow people to train it for their domain. and basically, provide them with several models. And the assumption is that they have a certain amount of their own training data, and they'll be able to figure out which of the models, which kind of composition of features through experimentation really works for their domain. So this is different from building a model from scratch to solve a new problem. But I do think that, I can't remember what term you coined, Jan.
Semi-competent data scientist, is that what you meant?
I think that, I think somebody that, if you have enough data and you have enough it's kind of like a little bit of a product line of a model where you give them kind of different things that they can compose together, and you experimentally guide them through the process, and they feed in the data. I think those are the kind of things that you don't need to have an actual expert to do. At least I'm hoping that's the case.
Yeah, I'm with you, because I mean there are two sides to this. One, of course, everyone wants to work with experts, but the number of experts that are out there is actually highly limited. People that have a strong data background and have the domain and the knowledge and are able to create the Python code that software engineers can then take. I mean, there are not that many around, and still there are many more problems to be solved by this kind of approach. So in some of the companies that I'm involved in, we're looking actively at low-code solutions that are more graphical in nature and that help people that are not as much of an expert to still work with their own data and create models that I think are interesting and relevant. We are starting, we have less than 4 minutes left, and we all know that we're going to get cut off rather abruptly. So what I was hoping to ask all of you is to provide a 30-second reflection or a main takeaway that you would like the audience to take away from the panel. Talk also a little bit about what you would like to see going forward, if you allow me, because I think it's if you could make really crisp what you're looking for, I think that would be incredibly valuable. And since we ended with Jane last time, maybe Jane, we ask you to go first if you want to do that. So 30 seconds.
I want to, but I will. So looking forward, I think the takeaway for me is that we need to understand the context in which these models are going to be deployed, and understand exactly how much, what explainability, what transparency kind of needs to be engineered into the system to make them usable by the people that are going to be deploying them and using them.
Good. Thank you very much. That was for the others 23 seconds. So if you keep it on the same length, that would be great. Brian, if I go in reverse order, I think you're next.
Sure. So I guess what I would like to see is some kind of realism and maturity emerging, and concepts that we have come to understand in software engineering, being like information hiding, for example, is a very useful mechanism for hiding complexity of design decisions, so you could just communicate with interfaces. The danger of doing that in a machine learning environment or with models that are making decisions that are not transparent is very significant. So some maturity where we had new concepts and new practices that are relevant for the challenges of this era, that would show more discipline, maturity, I think.
Okay. This was 45 seconds, a bit too long, but Barbara is very efficient, so I'm sure that she can, in 20 seconds, give her statement.
Yeah, I would like to essentially have more in future that users.
Oops, and that's where her internet connection broke, which is.
That saved my time.
Yeah, exactly. Ian, maybe you go next because Barbara clearly. Oh, sorry, Barbara, you're frozen.
Oh, sorry, this is very bad timing for my internet connection here.
Yes, sorry about that. We're gonna go to Ian, and you can put your feedback in the chat. Ian, 10 seconds.
Scalability. Jobs that run on petabytes don't finish in milliseconds. Make sure people understand this and understand the computational cost of doing such things.
Good. Thank you. Ipek, 20 seconds.
Actual demonstrations of changing anything changes everything principle. Does it really work that way? And what are some of the examples that we can actually point to?
Good. Barbara, if your internet connection works, I can give you 10 seconds.
Adaptability and more close interaction with the user of the system.
Excellent. Now, with that, there are a lot more questions. I want to wrap this up by thanking all of you for participating in the panel. I want to thank the audience for being so active in asking questions. I thought it was a very interesting and value-adding set of topics, and I think it's a good basis for running a future version of this event in about a year. And with that, we have 1 second left, and we are